We saw how to find antiderivatives of our very basic functions, the ones that we first learned about in Calculus 1, where we knew how to take derivatives of them, and we can go backwards and recover the original function. But as we saw also in Calculus 1, some functions may be a little more complicated. We have things to worry about like compositions, for example. So we know how to differentiate compositions of functions by the chain rule. That's our symbol, remember, the chain rule. So can we do the same thing going backwards? Well, it turns out we can using this method called substitution. Generally use substitution because that's the letter that we'll probably use most of the time, but it's just a change of variable to make a hard problem into an easy problem. So let's go ahead and look at some examples on how to use substitution to evaluate integrals, but first let's actually state the results. And I'm going to have us refresh with the chain rule here. So we're going to go ahead and look at this first with the chain rule. So if I want to take a derivative of a function inside a function here, so say the derivative of f of g of x, okay, this is the chain rule here. See? If I want the derivative of this composition here, I'm going to take the derivative of the outside function and then evaluate that at the inside parts. And then I'm going to multiply by the next link of the chain, which is g prime of x, the derivative of the inside. Okay, so as we saw, okay, as we can see, so for example, perhaps I want to take the derivative of, I don't know, x to the fourth plus e to the x to the 10th power. Okay, I'm not going to go ahead and multiply this out because nobody has time for that. Instead, we'll use the chain rule. The outside function is that power function. So something to the 10th power rule says it's going to be 10 times whatever to the 9th power. Okay, subtract 1 from the exponent when we do the power rule forwards. And then we're going to multiply by the derivative of the inside. And here we just use the power rule again. Derivative of x to the 4th is 4x cubed. And derivative of e to the x is e to the x. So that's how we take the derivative with the chain rule. Now, from every differentiation rule, there's a corresponding integration rules going backwards. So what if I take this first relation here? Okay, this is going to be our main idea here. What if I take this guy here and integrate both sides? Well, the right-hand side, I know is a derivative because that's the chain rule. The idea is that I'm going to change variables, okay? So if I want to integrate, say, f prime of g of x times g prime of x dx, the idea, okay, is to change variables. So I'm going to set u equal to g of x. Okay, I'm going to make this into an easier looking problem. Well, now I'm going to have to make a corresponding change in u because u is related to x. Dx is a small change in x. We need a small change in u. Du, okay? And so now we're going to take the derivative, okay? Get that differential, remember? So the derivative of g is just g prime of x, and then we have dx there for the differential. And now take a look at what happens here, okay? In orange here, I'm going to replace u with g of x, and then in red, I have du, which is g prime of x dx. That's all this here. And now take a look at what happens. Okay, this now becomes the integral of f prime of u du. I'm integrating a derivative, and so I get f of u plus a constant, and now I just go back into the original variable, the original units here, f of g of x plus a constant. So substitution allows us to make a hard problem easier just by changing variables and collapsing things down. So let's actually see this in action here. All right, so let's take a look at our first example here. I want to look at this integral, x times x squared minus 1 to the 99 power. I want to integrate this. Well, do you really want to write out 100 terms of this binomial expansion and then multiply by x? Well, think about it. You got to do, 99, choose 0, choose 1, choose 2. Binomial theorem, right, from algebra. But that's not a good thing. We want to make this easier for us, and that's what substitution allows us to do. The idea is that we're going to try to find a function and its derivative. Okay, we're looking for compositions. Okay, so one of the rules of thumb here for substitution is we want to look for a function and its derivative, and a lot of things will suggest what substitution to use. Okay, here I have functions inside a function. I have this thing here, I'll highlight it in red, this x squared minus 1 is inside this 99th power thing. That's an innermost function. Chain rule passes things through like that. We get links in the chain. And so now the idea here is we're going to set, well, first I'm going to set the pencil to correct, okay? So we're going to set u, we're going to change variables here. U equals x squared minus 1. And now we need the corresponding differential. So du is 2x dx, okay? We just take the derivative. Now, take a look here, okay? I'll highlight in blue, okay? Notice that in my integrand, I have x dx, okay? I don't have that 2. So there are a couple of ways that you can go about this. One of my favorite ways is to play for a match. And what happens here is that I just go ahead and divide both sides of this differential thing by a scale factor. In particular, I'm going to divide both sides by 2. So we get 1/2 du equals x dx. Okay, another thing that you can also do is solve for dx, so to say. So you can also write this as dx equals 1 over 2x du. And then you just make the replacements, okay? And now let's take a look at what happens here. So this integral becomes, so x dx is going to be 1/2 du, so 1/2 du. X squared minus 1 to the 99 now becomes u to the 99. Let's fix that a little bit. All right. And that's a much easier problem now. It's just power rule, right? So we have a 1/2 here. Add 1 to the exponent. 100, and then divide by 100. Plus a constant. But we're not quite done because I want to go back into my original units. Okay, I'm finding an antiderivative. I started with a problem in x, got to end with a problem in x. So we're going to go ahead and go back into the original units, and I'll replace u with what it was. That's x squared minus 1. So x squared minus 1 to the 100th power, all divided by 200. 2 times 100. And that's how we do a u substitution. Okay, we took a hard problem and collapsed it into an easier problem. All right. Let's take a look at another one here. Okay, we're going to integrate x plus 3 over the square of x squared plus 6x dx. Now, this may look a little scary, but again, let's think about our idea. We want to spot a function and a derivative up to a scale factor. And some ways that we can look for substitutions is we're going to look inside innermost functions. Another thing to spot is to think about if you have a fraction like this. Okay, whatever is in the denominator is probably going to be your u sub. Okay, so, but in fact, we're going to go deeper, literally, than that. We're going to take just this thing on the what's being squared in the denominator. That's going to be your u. So we're going to go ahead and set u equals x squared plus 6x. And by the way, you don't always have to use u as a substitution variable. You can use whatever letter you want. It's just convention here. Okay. And so du is equal to, well, take the derivative here. Derivative of x squared is 2x. Derivative of 6x is 6 dx. Okay. And notice here that I can factor a 2 out of here. Okay. 2 times x plus 3 dx. Okay. And why does that help me? Because notice here, okay, I'm going to get what are probably going to be called these du earmuffs. X plus 3 dx. I can solve for x plus 3 times dx in the substitution. Okay, let's go ahead and highlight the part that I want here. I can go ahead and solve for this again by doing that scale factor thing, playing for the match, dividing by 2. So I get 1/2 du, okay, du over 2 equals x plus 3 dx. Okay, now let's just go ahead and replace everything. All right, so x plus 3 dx is 1/2 du. Okay, then what do I have left over? I'm going to have a 1 over x squared plus 6x squared, which is now u squared. And this is now an easy integral. Okay, remember from the power rule, well, first let's put that 1/2 out front. We can push it outside. I can think about this as u to the minus 2. And now I'm just going to use my power rule, right? 1/2 times u to the minus 1 divided by minus 1 plus a constant. And after we go ahead and tidy everything up, we'll have a minus 1/2 times our u here, which is x squared plus 6x. And then, of course, plus a constant, and we're done. Okay, so again, that's how the substitution rule works, okay? It's the chain rule in reverse, okay? We're unlinking the chain. We're getting an easy problem out of a hard problem. Okay, again, watch out for your exponent rules here. All right, let's keep going here. Here's another interesting one. Integrate x cubed times the square root of 2 plus x to the 4th dx. Again, we want to look for a function in some form of its derivative. Note that inside the square root, I have a 4th power, and on the outside, I have a cube. So the innermost thing is going to be my substitution. So we're going to have u equals 2 plus x to the 4th. And so when I take the derivative on both sides, when I get that differential, du is 4x cubed dx. Let me fix that there. 4x cubed dx. Okay, and now notice that I don't have a 4 in my original integrand, so I'm going to play for the match here. Okay, du over 4, I'm going to divide by a scale factor, solve for x cubed dx, or you can just solve for dx straight up. Okay, it doesn't really matter. Okay, they're both schools of thought. And now I'm going to make my replacements here. So my integral now becomes, so x cubed dx is now 1/4 du. And now I'm inside the square root, I just have a u, square root u. Okay, how do we work with square roots? We use the power rule, okay? So we're going to go ahead and write this as u to the 1/2. We'll do this just as a reminder. Okay, so we have 1/4 times, so think about it. So we're going to add 1 to the exponents. u 1/2 plus 1 is 3/2. Let's fix that. Divided by the new exponent, plus a constant. And now we got to do some fraction stuff, okay? Multiply by the reciprocal, 2/4 times, let's see, well, let's be a little careful here. 1/4 times 2/3. And now u to the 3/2, okay, that is now just what our u was, 2 plus x to the 4th to the 3/2 plus a constant. Okay, and after we tighten this up, we will get, let's see, 2/12 when we multiply the fractions, so that's 1/6 times 2 plus x to the 4th all to the 3/2 plus a constant. And folks, that's it. See, this is just the idea with substitution, right? We're turning a hard problem into an easy problem. Let's keep going here. All right. Integrate x over the 4th root of x plus 2 dx. All right. So I have a fraction. I also have a root in there. So I'm going to go innermost. Okay. So I'm going to set u equal to x plus 2. Okay. Just the stuff on the inside of the square, on the 4th root there. And that means du is equal to dx. Okay. Now the thing is here, if I just go ahead and replace stuff, I know how to replace x plus 2. All right. I know how to replace x plus 2. But how do I replace just that x? Well, to take care of this x here, I'll go ahead and highlight this in this bright green here. Take care of that x, okay? I'm going to take my original substitution and solve for x, okay? X is equal to here, x is u minus 2. X is u minus 2, so I'm going to replace that x in the numerator just by u minus 2. Now, after I do everything here, what do we get? So we'll have the integral of, so x dx, so x is u minus 2. In the denominator, I have the 4th root of u du. Okay, now we're going to have to do some fraction stuff, okay? So we have stuff over a common denominator. Remember that a plus b over c is the same as a over c plus b over c. So we have u over the 4th root of u minus 2 over the 4th root of u du. Okay. And now we're just going to do some fraction, some exponent rules here, okay? Remember, okay, let's go ahead and refresh ourselves here. So when I have x to the m over x to the n, I'm dividing with the exponents, I subtract the powers, okay? And so the idea here is that u over the fourth root of u is the same as u to the 1 minus 1/4, okay? And then we're going to take that 1 over u to that 1 over u square, this is hard. 1 over fourth root of u as u to the minus 1/4. Again, just elementary exponent rules. All right? So when we do all that stuff, I'm going to go ahead and leave it to you to verify. We'll have the integral of u to the 1 minus 1/4, that's 3 over 4, minus 2 times u to the minus 1 over 4. And now we're right back to the power rule. Okay, so when we go ahead and do everything, we'll have u to the 3/4 plus 1, that's going to be 7 over 4, okay, divided by 7 over 4, minus 2 times u to the minus 1/4 plus 1, that's 3 over 4, divided by 3 over 4, plus a constant. All right, now we're going to go ahead and put everything back in terms of the original variables and clean everything up. So divide by 7 over 4, that's multiplied by the reciprocal 4 over 7 times, okay, u was what again? X plus 2 to the 7 over 4 power. Okay, then minus 2 divided by 3 over 4 is the same as 2 times 4 over 3. That's 8 over 3. Verify that. And then times x plus 2, 3 over 4, plus a constant. Remember that constant of integration. Okay, so this one had a couple of things going for it. Okay, but the idea here is that you want to make sure everything in your integrand is in the new variable when you change variables, when you change units. Okay, so something like this. If you have u equals something, you can, if you need to, solve for x. X is a function of u. All right. A couple more for this part here. I want to evaluate this thing here, the integral of t times sine of t squared dt. Okay, now you'll probably notice that like a lot of these that we're looking at are products, and yeah, the chain rule comes up with products, but you know, the idea here, again, you want to turn a hard problem into an easy problem. Well, look at the arguments, the angle of the sine that we're looking at. We're looking at the sine of t squared. Well, what's the derivative of t squared? It's 2t. Now you have a lone t just sitting out front there. So again, we're going to look in the innermost function. Okay, we're going to set u. Actually, let's go ahead and make this a little interesting here, because my u's and my fourth were getting a little squirrely there earlier. New variable, y equals t squared. Okay, again, you can use whatever letter you want. Set y equal to t squared. So dy, the differential, take derivatives on both sides, 2t dt. And now you play for the match, okay? Solve for dt, however you want to think about it. Okay, so I have 1/2 dy is equal to t dt. Take a look here, my du earmuffs, okay? My dy earmuffs here, okay? That's now going to be 1/2 dy. Now we're going to put everything in terms of y. So I have the integral of 1/2 sine of y dy. I can shove the 1/2 up front as a multiplier. And what happens here, okay, the antiderivative of sine is minus cosine. Okay, remember your basic pairs. Don't mess up your sines, your sines, and your sines, signs. Now put everything in terms of the original variable. So y is t squared. We have cosine of t squared there, plus a constant. Of course, how do you check your answer? You take a derivative. Here you just use a chain rule, right? Derivative of cosine is a negative sign, so minus times minus is plus. And then derivative of t squared is 2t, the 2's will drop. Okay, verify that for yourself. All right, now this one's really interesting here, okay? The integral of the cosine of x times the cosine of the sine of x. Now that looks a little scary, okay? We might have to do a few things here, but go ahead and think about it, right? I'm going to give you folks a second to see what the move is here. All right. Again, we want to look for these compositions, right? Look for the innermost function, and you see that I have a sine inside of a cosine. So in this position, we're going to set, I'm going to call it again y here. Y equals sine x. And that's just brilliant, isn't it? Y equals sine x. All right. Differential, that's the next step. So dy, take the derivative, is cosine of x dx. Take a look at what I got here. Okay, cosine of x dx here. All right, so now we're just going to go ahead and make everything in terms of the new variable. So I have the integral of cosine of sine x, but sine x is y. So cosine of y is dy. But dy is cosine x dx. Now we're back to a basic one. Antiderivative of cosine is sine of y. Okay? And then just go back to the original variables. Sine of x plus a constant. Okay? You can always double check your answer by taking a derivative. Okay? Let's see. We got a few more here. Okay, and then we'll end the part here. 1 over x log x. Again, okay, we want to look innermost. We want to think about the denominator here. My denominator here is x log x. Well, okay, that doesn't really quite help me because, well, the derivative of x log x requires a product, and I don't see any extra stuff here that might require that. But let's think here. We recall, okay, that the derivative of log x is 1 over x. And you see I have a 1 over x kind of hiding in there. And so if you see it, all right, we're going to set u, okay, our new variable is going to be log x. So du is 1 over x dx, and now take a look here. If you take a look, I have 1 over x dx. That's my du. Very clever here. So now I'm integrating 1 over u du here. Okay, well, that's stuff that I put in the highlight blue-violet color. Okay, whatever that is. That's all my du. And what is this? It's up there. And of course, remember that when we integrate 1 over u, we have to have log of absolute u. Okay, so we have the log of the absolute value of u plus a constant. And so this comes out to be the log of the absolute value of log x plus a constant. Okay, required a bit of extra thinking, but there you go. All right. Here's an interesting one. Okay, integrate arctan x over 1 plus x squared dx. Okay, remember, that's not tangent x to the minus 1 power. Okay, that's inverse tangent. Okay. Well, we have another relationship that we can use here. Okay, think about innermost functions or think about things that might appear. Well, I know that the derivative of arctan x is 1 over 1 plus x squared. And so what do you think my u is going to be? Well, u is going to be arctan x. And du is going to be 1 over 1 plus x squared dx. This one is as great as they come, okay? So, then we do all the replacements here. Okay, let me go ahead and highlight what my du is. That's dx over 1 plus x squared. I'm just integrating u du. That's another basic one, right? Think about the power rule. You have the power to rule, right? Add 1 to the exponent, divide by the new exponent. U squared over 2 plus constant. Well, what is u? U is arctan. So arctan x squared, okay, times a half there, plus a constant. That's all there is to it. Okay, hopefully you're seeing these patterns. Find a function and its derivative up to a multiple. Get everything in terms of the new variable. Find the easier antiderivative, okay, and then, boom, put it back in the new variable, old variable. Okay, now we haven't seen some of these yet, but like you may need to do multiple substitutions. You just unravel them, okay? Do as many as you need, okay? Work one step at a time. And I think that's our last example for this part. So we've seen some very elementary examples of how to do u substitution, how to change variables, how to integrate hard problems by turning them back into easy problems. Notice that we didn't talk about definite integrals yet. And then the next part, we're going to go ahead and look at a couple of examples where we have definite integrals and the one extra thing that you need to do. and I'll see you in the next one.